So it's a great pleasure, of course, to introduce my old friend Senthil, who's a professor at MIT at present. Senthil is a product like many of the others we know in our own department from IIT Kanpur, getting his degree there in 92, and then a PhD at Yale with Subir Sachdev in 97. After that, he was a postdoc at KITP, and then joined the faculty at MIT in 2001. And he's extremely well known in condensed matter physics for his many innovative ideas, in particular, the whole theory of deconfined criticality that became a sort of a cottage industry in its own right in the early parts of, well, this century, so to speak. At present, Senthil is a Simmons investigator and has been so for almost a decade. He was a distinguished visiting chair at the Perimeter Institute, and he's a fellow of the American Physical Society. But those of us who know him well know that this is only a small sort of token of appreciation everybody has for him, and it's really a pleasure listening to him, and I'm going to enjoy today's talk, I'm sure. So over to you, Senthil.
Well, thank you so much, Kedar, for that very kind introduction, and thanks to Rishi and Kedar for inviting me to give this talk. So it's a real pleasure to be able to give this talk to the TAFR theory community. I've always enjoyed my visits to TAFR, sort of regretting that in the last couple of years it's not been possible to come. Look forward to future trips once the pandemic is truly done. Yeah, so let me get started on my talk. I'll explain what this title of strange quantum metals means as we go along. So the talk itself is based on work that's reported in some of these papers, primarily with Dominic Els. So let me introduce my collaborators. What's going on? There. Oh. Okay. No. So Dominic was a postdoc with us at MIT for 3 years before he moved on to a position at Harvard, and in a few months he'll be a professor at the Perimeter Institute. We also collaborated a bit with Ryan Thongren, who's a postdoc at KTP, but previously a postdoc at Harvard. And more recently, we've been working with a student, Zhengyan Shi, of mine at MIT, and a postdoc, Hart Goldman, also at MIT. So I have to say that this crew of people that I work with have been incredible, and they've led many of the ideas, and I'm sort of coasting along, thanks to the collaboration with these brilliant young people. Okay, so how many of you know anything about condensed matter physics? Maybe you can raise hands or something. Or the people who are willing to admit that they don't know any condensed matter physics. No, Radhi, you know condensed matter physics.
I thought it was for the first one who knows something about.
Oh, I see. Okay. All right. So all right. Very good. Yeah. No. Good. I'm happy to see that a few hands up on because it's often true when you go and give colloquia that people typically may not know very much about even the broad subject area that the speaker is speaking about. So I thought I would start with a quiz. So here's a picture. How many of you recognize, does anybody recognize what this is a picture of? And Kedar and Rajdeep are the last people who should answer. Anyone wants to make a guess?
Fermi surface of copper.
It's the Fermi surface of copper. Vikram. I should have said that Vikram is not allowed to talk either. The Fermi surface of copper discovered in this Fermi surface shape was nailed down in Vikram's alma mater 60, 70 years back, maybe longer than that, by the person called Pepard. But anyway, so the Fermi surface will figure prominently in my talk. So I thought this may be a good place to get started. Okay, so in a conventional metal, the theory that describes what happens, the rough sketch of it is as follows. So in a metal, electrons move around freely. That's what we learned from high school, and that's what gives metallic conduction. Now, once you learn some physics, you recognize that electrons in a metal should be treated as a quantum fluid of fermions. In particular, the Fermi statistics is important at, to understand the electronic properties of a metal. That's because given the densities of the electron fluid inside a metal, the degeneracy temperatures are extremely high. They are tens of thousands of Kelvin. So at any ordinary temperature, you're well below the degeneracy temperature, and you better treat the electrons as fermions, right? So so quantum mechanics matters for describing the physics of a metal. Now, the electrons are moving around, but they also repel each other due to the Coulomb repulsion. And the strength of the Coulomb repulsion is not small compared to the electron's kinetic energy. But despite that, its effects are somewhat weak. And one of the main reasons why the effect of Coulomb repulsion is weak is because of Pauli exclusion. In real space, you can think of it by saying that at least light spin electrons don't come too close to each other because of Pauli exclusion. But a better picture is to think in terms of momentum space. And in momentum space, the free Fermi gas, of course, has a Fermi C, and states inside the Fermi C are completely rigidly occupied. And any extra electron that you add that lives outside the Fermi C, the phase space that's available for scattering is dramatically reduced compared to what it would be in free space, right? So all these states inside the Fermi C are taken out of the available final states for scattering, right? So the important quasi-particle states that live near the Fermi surface, they only scatter weakly off each other, and then you have a picture of the electron fluid in a metal as more or less free Fermi gas with some fairly simple residual interaction that you can deal with, but no real important scattering. And the scattering is some weak perturbation to the basic theory of this fluid. And you can then base your understanding of electrons inside a metal in terms of this free fermion picture, right? And this picture describes conventional metals extremely well. And it's formalized in the form of a theory known as Fermi liquid theory, which is due to Landau. So it's called the Landau's theory of Fermi liquids. And this theory describes most metals extraordinarily well. It's one of the big successes of 20th century condensed matter physics. Okay. Okay. Now, I'm going to be talking a lot about electrical resistivity of metals. The electrical resistivity is one of the easiest things for experimentalists to measure. You just, at least, if you're a theorist thinking about resistivity measurements, you just say that you connect some two leads, run a current, and measure the voltage, right? So that's all there is to it. In real life, it's a bit more complicated, but it's still very easy to measure the electrical resistivity. So in a conventional metal, if you measure the resistivity versus temperature, you'll find a curve that looks something like this, right? So the zero temperature value is non-zero, and this comes from elastic scattering of electrons off of defects in the crystal. It could be impurities, it could be missing atoms, things of that sort. And the temperature dependence comes from inelastic scattering of electrons from phonons, from other electrons, from anything else that moves, that can move inside the solid. Now, in the situation in which the main inelastic, the dominating inelastic scattering is the electron-electron scattering, I said that this is weakened by Pauli exclusion, but still it's not zero. And if this electron-electron scattering dominates the relaxation of electrical currents, then one finds that the temperature dependence of the resistivity is quadratic. Okay, it's T squared. And this is seen in many sufficiently strongly interacting Fermi-liquid metals, where the electron-electron interaction dominates the resistivity, the current relaxation. And the reason for this T squared is there's a very simple phase space reason why the scattering rate goes like T squared. So it's really the process in which two electrons come in, interact through the Coulomb interaction, and scatter off each other. And the phase space consideration is goes roughly like this. So if you have an electron that is trying to scatter at some energy epsilon, which is of order kBt, the temperature. So this electron needs to scatter off some other electron, and the other electrons are all living inside the Fermi sea. So it needs to pull an electron out of the Fermi sea and give it some energy, and thereby in that process, this first electron will lose some energy. Okay, so the amount of energy that this first electron has to lose, right, its energy budget, is its total energy, which is kBt. Right? It's total energy above the Fermi energy, which is kBt, right? That means that the electron that can be pulled out of the Fermi sea must be within kBt of the Fermi energy, right? And then the electron that it can scatter into, the place that it can jump out into once it gets kicked out of the Fermi sea, it can at most, since it can at most gain energy kBt, this final electron that also has to have an energy that's within kBt of the Fermi energy, right? So the fact that both this initial and final electron have to live within kBt of the Fermi energy tells you that the number of states, the number of scattering processes that are allowed will go like the square of kBt. And that's the reason why you usually get kBt squared, T squared as the scattering rate for this process. Okay. Okay, so that's the story. Now, in the last 30 plus years, there are many, many metals that have been found to violate Fermi liquid theory, sometime down to extremely low temperature. So low means low compared to the natural energy scales that characterize the system. So the most prominent example, perhaps, is the is the parent metal of many high temperature superconductors. Now, probably many of you have seen the phase diagram of the high temperature superconductors a million times in the other colloquial talks. So, the copper-based high-temperature superconductors, the most famous ones, they start off as insulators, and then you add charge to those insulators or remove charge to those insulators, and you end up with a superconductor. But as this phase diagram shows, as if you go above the superconducting transition temperature, the metallic state that you get turns out to be extraordinarily strange. I'll show a little bit of data. It's strongly believed by basically everybody, by most of the people thinking about this problem, that this metallic state is not a Fermi liquid for various reasons that have been forced upon us by experiments. And you see that the stained metal occupies a wide range of the phase diagram, right? And so clearly there's an important problem to try and understand. You can't declare victory on any story of high temperature superconductivity without confronting the nature of the strange metal, right? This is the state from which superconductivity emerges. So if you make up any story for the mechanism for the superconductivity as it emerges from the normal state, without giving a story for what the normal state is, there's, people are bound to not be convinced, right? So it turns out this is not the only example, though this was one of the first examples. There are by now many, many metals. For instance, there's a class of metals that if you tune them near to a phase transition to magnetism at zero temperature, they also show non-Fermi liquid physics. Now, some of you may have heard the recent excitement in condensed matter physics on Moiré materials, graphene in twisted bilayers of graphene and other systems. So even here, even in this system, it turns out that you get wide ranges of strange metal non-Fermi liquid like physics. Okay, so it's there in a lot of different places, and so one needs to understand it. So let me talk a little bit about these copper-based high TC materials, the same phase diagram that I showed. So these materials are all the important, they are layered materials. They have layers of copper and oxygen separated by other stuff, right? And all the interesting electronic physics happens within these copper-oxygen layers, right? Now, if you go and measure any property in this regime, what people find are power laws, and those power laws are distinct from what you expect in a Fermi liquid. Now, it's known that through variety of measurements over the years that like ordinary Fermi liquid metals, in the stained metal regime, there's a sharp Fermi surface. The Fermi surface still is well defined, but you lose the concept of a sharp Landau quasi-particle. Okay, so the electron doesn't exist as a quasi-particle anymore. Apparently, it doesn't exist as a quasi-particle anymore in this regime. So somehow the notion of the Fermi surface itself continues to make sense. So here's an example of the measurement of the electrical resistivity of one of these materials. So I should say that these copper-based high TC materials, which I'll refer to them as the cuprates, that's the standard terminology. There's no single material, rather it's a family of materials. What they all share are these copper-oxygen sheets, copper-oxygen layers. There's the stuff that you put in between can be varied, and that gives rise to different kinds of members of the same family. Okay, that family is collectively referred to as the cuprates. So if you measure the resistivity within the layer of, this is a famous measurement from 1990 of one of these cuprates as a function of temperature. So you find something that doesn't at all look like what I showed you here, right? Doesn't at all look like this. It doesn't follow this T squared law. Rather, you get something that's just linear. And it's linear in this data all the way from 10 Kelvin to about 800 Kelvin, right? With no change of slope. So this was one of the striking and continues to be one of the really striking indications that it's not, something that a different kind of theory is needed. Okay, so there's a grand challenge in quantum condensed matter physics. The more general question is, how should we think about metals where the quasi-particle concept has broken down, right? So there's many questions one could be asking in this direction. So one question that I've been particularly interested in is the nature of a coarse-grained, that is a long wavelength, low energy theory of the stained metal. So of the kind that in quantum field theory, many people like to say call an effective field theory, which doesn't really keep track of the details of the microscopics, but tries to give a universal description of the low energy properties of the system, right? More generally, this is a concept that's familiar to all physicists. If you think about, say, hydrodynamics and think about the Navier-Stokes equation. So the Navier-Stokes equation describes all fluids, irrespective of what atoms make up that fluid. the only input from microscopics that one needs are values of a few constants like the viscosity or the compressibility or things of that sort. But the equations themselves hold for all fluids, right? So we may hope that we can find a similar coarse-grained universal long-distance description, low-energy description of various classes of strange metals, right? And so that's a broad question that I'm interested in. Okay, so to go towards that, so a couple of years back with Dominic Els, we articulated a set of assumptions about a class of strange metals. And this class will include some of the most prominent strange metals that are seen in experiments, the cuprates and some of these systems that are tuned to close to a zero temperature magnetic transition. Now, for fun, we decided to colloquially call our assumptions our central dogmas. So let me go and describe what the assumptions are. The first assumption is that the physics of the strange metal is that of a clean system, that the essential physics does not involve disorder, which is inevitably there in any real solid. Imperfections in the crystal, extra impurities that you have, and so on. The second dogma is that the physics is scale invariant. For instance, that the electrical conductivity measured as a function of frequency and temperature satisfies a scaling form where all the data measured as a function of frequency and temperature can be collapsed onto this form where it's 1 over temperature times some function of omega over t at omega and t that are small compared to all the microscopic energy scales. So this assumption means that there's no intrinsic frequency scale. So the scale for the frequency here is simply set by kBt over h bar. Okay. And the third dogma is that this metallic state is what we call compressible. That simply means that it's not tied to any particular charge density. Okay. So why these dogmas is addressed in the next few slides. So I'll give more detail on the reasons for making these particular assumptions. So why these dogmas, right? So as I'll argue in the next few slides, these are well motivated by experiments on prominent strange metals, for instance, the cuprates. So the cuprates have a big advantage compared to other materials because they're some of the most intensely studied systems experimentally in solid state physics. So any experiment that you hope has been done in some material will typically have been done on the cuprates, but maybe not in other class of materials, right? So, so that's one of the main reasons to focus a lot on the cuprates. There's a lot more experimental information that's available on the cuprates than on other materials. Okay, but even aside from experiment, it's interesting theoretically to make these particular assumptions. The assumptions we made are mild assumptions, but they still constrain the theory extremely strongly. And hence, we narrow down the search for an explanation, right, to a narrow class of theories, right? So that's the second reason to make these assumptions. We don't want to assume too much, right? Because then, you know, whatever we learn will be a property of the assumptions we make and not of the real system. We don't want to assume too little because then we can hardly reach any conclusion, right? But you know, just making these three assumptions seems like, as we'll see, leads us to fairly strong results. Okay, so let me start by giving the empirical support for these three assumptions, right? So let me start with clean. In a sense, this is the hardest assumption to to justify, because after all, disorder is there, right? Impurities are there. In the cuprates, for instance, the superconducting materials, the metallic systems are produced by a process called doping, where you introduce, for instance, you take a material like lanthanum copper oxide, which is one of the cuprate materials, and you substitute, you replace some of the lanthanum atoms with strontium, and these strontium atoms go and sit at random locations in the crystal, right? So you necessarily have random impurities, and it's a process of doping with these strontium atoms that gives rise to the charge, the extra charge density that enables the system to be a metal or a superconductor in the first place, right? So there's no way that's currently known in the cuprate system to introduce metallic behavior, to introduce dope, charge density, which gives rise to the metallic behavior without also introducing disorder, right? But nevertheless, I want to go ahead and argue that the essential physics of the strained metal does not involve disorder. Let me show you more data on the electrical resistance. Yeah, sure.
So in that sense, would you say that this set of models or phenomena or explanations that you are trying to give us is kind of runs counter to the SYK way of thinking about it? Is that a correct thing to say?
Yeah, I'm exploring something different from SYK. Yeah.
So
that's right. Okay. Yeah, I can comment more on it later. Yeah. Okay. But yes, the zeroth order indeed. Yeah. Yeah. So let me show you more data on the strained metal transport in the cuprates. So as I said, there are many. There's a family of materials, and these different materials all share the same copper oxygen plane, but what's between the planes is different, right? So here's a measurement in one of the cuprates, and you can forget about this data. This is at very low charge density, very low doping. The important data is here, the linear resistivity. So you see it again going up to several hundreds of Kelvin, all the way now from TC up to several hundreds of Kelvin. Already showed you this data, right? And so you may worry that the strained metal, this linear resistivity only goes up to TC, and these are high temperature superconductors. So do we really know that this is a property of the very low temperature state? So here's some relatively modern data where what was done was to suppress the superconductivity with a magnetic field to extend the data from the normal state down to very low temperature. And here the linearity goes down to about a Kelvin, right? Which is extremely small compared to the intrinsic energy scales of this system, which are like around 1500 Kelvin or even higher, right? So there's one energy scale at 1500 Kelvin, and there are other scales which are even higher, right? So 1 Kelvin is extremely low compared to those scales, right? So it just stays linear down to that. And here's yet another material where you nicely see linear T behavior. Okay, so it's seen not just in one cuprate, it's seen in every cuprate, right? Now, remember I said that the zero temperature resistivity, the residual resistivity, comes from the elastic scattering of impurities, right? Now, it turns out that the residual resistivity can be very, very small or even absent. So here I just drew a straight line on this data. This is one of the cleanest cuprates that exist. I drew a straight line, and you see that the intercept is basically zero, right? And so the fact that you look at the linear resistivity in the cleanest of cuprates, you find the residual resistivity has been suppressed to zero, suggests that perhaps disorder is not essential to the basic physics, okay? Because the residual resistivity is something that comes out of disorder scattering, impurity scattering. Now, there's a different kind of interesting evidence for the unimportance of the disorder. So if you compare the slope of this linear resistivity in different cuprates, and you have to be careful on what you compare for, because some of these cuprates have different number of copper oxygen layers. So you have to look at what's called the resistivity per copper oxygen layer, what people call the sheet resistivity. And you look at the slope across different materials, and the slope is this number, and it's in ohms per Kelvin. And you see that it's basically the same for different cuprates, right, with an error bar, right? So I pulled this out of this recent paper, not quite recent anymore. The main focus of this paper was on something else, but I want to draw attention to this aspect. So these are different materials. They share the same copper oxygen plane, but they have other stuff in between. They are grown differently, you know, they're grown by different labs. So among other differences, they certainly will have varying disorder strengths, right? It's hard to imagine that these materials grown by different people and using different methods with different chemicals all have exactly the same kind of disorder, right? So the fact that they have the same slope strongly suggests that the slope doesn't care about the kind of disorder that you have or the extent of disorder that you have, okay? Consistent with the absence of a residual resistivity in the cleanest cuprates. Now, finally, there's an obscure but very important experiment that was done a while ago in 2000 that's very interesting, that also speaks to the same issue. So people had studied certain cuprate, one of the prominent cuprates, by exposing it to electron irradiation. Now, this is a very gentle way to increase the level of disorder in the system. The radiation leaves some tracks behind, and the electrons scatter off those the resulting defect lines. So what you see in the data is that, so it's all done in the same sample, and 0, 1, 2, 3 refer to the data taken on after different exposures to the irradiation, right? Different exposure times, right? So the slope doesn't change, but the intercept changes, right? The curves move parallel to each other, right? So you're increasing the disorder by increasing the irradiation time, and you're not changing the slope. The only thing you manage to change is the residual resistivity, right? This again strongly suggests that the slope is insensitive to disorder, right? It's not just the slope is insensitive. That combined with the previous thing, my previous observation, these two. So this seems to tell you that the slope is insensitive across different samples to, among other things, the level of disorder. And here, in the same sample, it's insensitive to the level of disorder, right? So all of these motivates the assumption that the essential physics of the stained metal can be understood through a lattice translation invariant model, okay? Even if in real life, there are impurities, you can worry about impurities as a correction to the essential physics. Okay. So let me turn to the second dogma, that of scale invariance. You know, first, as I said, people measure all kinds of power laws in this stained metal regime, which indicate, strongly that there's some sort of scale invariance. But let me talk specifically about transport, about electrical conductivity. So part of the assumption is that the stained metals transport will, in an ideal sample, extend all the way down to zero temperature, at least if you tune to some critical point or something. And this is supported by the resistivity data that shows linear T resistivity down to zero temperature if you manage to suppress the symmetry with the magnetic field, as people have done in some samples. So So let me show some of the evidence for conductivity scaling. It's a bit complicated. So this is a plot of the real part of the conductivity, the dissipative part of the conductivity, as a function of, you should just think of this as frequency. The first thing you notice is this long tail, and this tail goes up to about an electron volt. It probably has nothing to do with any delicate low energy physics. So the focus is going to be on what happens at lower frequencies. And here, what these authors did in 2003 is to make a plot of 1/kBt times sigma of omega. Yeah, that's right. Versus the scaling function, the scaling argument, h bar omega over kBt. And the data collapse is not great, but it's not bad either. And you see that it fits some sort of data collapse up to about 1.5 times the temperature. Beyond that, you run into this polar law tail, which probably has nothing to do with quantum criticality. There's much better data by now. Just last week, there was a nice paper from the Netherlands showing better scaling data for omega over t scaling. But the best data that currently exists is not in the cuprates, but it's in a material called ytterbium rhodium silicide, which is also a stained metal system. So very recently, again, not so recently, I guess, there's data showing much better scaling collapse of the in the conductivity as function of omega over t. Okay, so that's the level of evidence that exists. It's hard to take this data. You have to look at multiple frequencies, multiple temperatures, but people have been working on it, and the evidence supports making this as an assumption rather than, so that's why I want to make it as an assumption rather than claim that it's a fact. Okay. And the third assumption of compressibility, that it's not tied to any specific charge density, is not really doubted by anyone in the field. The charge density of the putative stained metal in the cuprates can be tuned by pressure. There are experiments that those kinds of experiments have been done. So in general, most metals are compressible. It's very hard to imagine an incompressible metal. So I'll continue to make this assumption that the metal is compressible. So for the rest of the talk, I won't really show much data. Actually, I won't show any data. I will take these for granted and ask about the constraints that follow on the low energy theory. Okay. So let me start with some general statements on electrical transport, right? And particularly the role of conservation laws. So electrical resistivity in any system requires a mechanism for electrical current to decay. Okay, if currents can't decay, you can't get resistivity. Now, if an electrical current can mix with a conserved quantity, then typically the DC conductivity will be infinity. Now the reason is can be argued as follows. Suppose you take a metal and you turn on a pulse of electric field, right? A narrow pulse of some width, right? Centered at time t equals 0. Now the current will respond in some way. When the electric field is 0, the current will be 0, and then it will increase, and then it will start, once the pulse has died down, the electric pulse has died down, the current at later times will also die down. But whether it can die to 0 or not depends on whether in the process of, in the process of setting up the electrical current, you also triggered the non-zero value of some conserved quantity, right? So if the current can mix with the conserved quantity, it may have triggered a non-zero value of that conserved quantity, in which case the current can never quite decay to 0, right? The conserved quantity its change value will just live forever, and that in turn will correspond to a small non-zero, to a non-zero current. So if the blue curve looks like this, and you take the Fourier transform of this picture, and this may be a good homework exercise for beginning graduate students. So then the Fourier transform of this picture will reveal that the real part of the conductivity as a function of frequency necessarily needs to have a delta function, right? And this J infinity, so if it has delta function, that means the DC conductivity is infinity, right? Now this J infinity, if it's non-zero, it exists only because of mixing with this conserved quantity. So in other words, you change the equilibrium of the system from what it was to something else with a different non-zero value of some conserved quantity, right? So this really is an equilibrium current that is going to be determined by some thermodynamic susceptibilities, right? So if your system can sustain such an equilibrium current, then its conductivity, its DC conductivity necessarily has to be infinity, right? And this is a familiar phenomenon in standard Fermi liquids, which with conserved momentum. If the current can mix with the momentum, then you will get infinite conductivity. And the low temperature conductivity of clean Fermi liquids is then determined completely by momentum dissipation that comes from operators that transfer momentum from the electrons to the lattice. Current spider physicists call this Umklapp operators, but it's these processes that dissipate momentum. In the absence of impurities, the only way you can dissipate momentum is by transferring momentum from the electrons to the lattice, right? Now, in more general examples, the current operator J will overlap with all operators that have the same symmetry and that are conserved typically. And these will generally lead to a delta function contribution to the conductivity and hence no DC resistance. Okay. Now the strained metal. So let's talk about the implication of this omega over T scaling that we've assumed, right? And for which there is some evidence. It's useful in thinking about what's going on at low energy to organize our thinking in terms of what some of you may be familiar with. That's, from the point of view of what's known as the renormalization group in quantum field theory and Kenneth Schmider physics, we like to think about what happens in terms of the fixed point theory and its perturbations. So if you don't know what the renormalization group is, just think about the low energy physics as being described by a theory that's completely scale invariant, plus some irrelevant perturbations that weakly break the scale invariance, right? Now, this omega over T scaling, when present, what it tells you is that the strained metal transport is a property of the scale invariant fixed point theory itself, and it's not determined by the irrelevant perturbations. Okay. So this conclusion is something to keep in mind. As I go through the rest of the talk, I will refer back to this conclusion again a few slides later. Okay. The strained metal transport is a property of the scale invariant theory itself and not determined by the relevant perturbations. So in particular, the scale invariant theory doesn't have a delta function conductivity, and this famous phenomena like the linear resistivity are not determined by slow relaxation of nearly conserved quantities, but is an intrinsic property of the fixed point theory. Okay, so since conservation laws play a huge role in determining transport and conservation laws related to symmetry, we need to think about the symmetry of the strained metal. So before I do that, let me make some general remarks on global symmetry in quantum many-body physics. So we have some microscopic theory, which I'll call the UV theory, that will have some global symmetry group, GUV. And we'll have some low energy theory that I'll call the IR theory. And this theory will, in general, have a different global symmetry group, GIR. And there's a map between these two symmetry groups, GUV and GIR. So I'm going to be interested in situations in which GUV is not spontaneously broken in the IR. I'll explain why. Of course, GUV could be broken spontaneously, but I'm not going to be interested in those situations, right? Okay. Now, so GAR could be bigger than GUV, in which case we say that the IR theory has emergent symmetry, right? Symmetry that's not present in the microscopic theory. Most subtly, this emergent symmetry group, GAR, may have a property known as an 't Hooft anomaly that's familiar to quantum field theorists. Perhaps the simplest example that some of you encounter in graduate classes on quantum field theory is the chiral anomaly or the axial anomaly of the massless Dirac fermions in 3+1D. And this anomaly will be constrained by the UV theory in some way. Okay. Now, anomalies or topological properties of how symmetry is realized in a quantum many-body system. They are robust to deformations within the same phase of matter. So this is actually interesting because it leads to a connection between study of topological phase of matter in condensed matter physics and lessons we learn from the study of these topological matter will then inform studies of non-topological phase of matter like non-Fermi liquids, right? So it turns out that all this interest in topological matter and condensed matter physics in the last 15 years has actually pays huge dividends for us ongoing attempts to understand things like non-Fermi liquid metals. Okay, so let me discuss the UV theory. It's a lattice model of electrons at some filling mu per unit cell in these space dimensions. And the UV symmetry group, I'll take it to be U1 charge conservation and lattice translation, nothing else, right? So I want to consider low energy states, ground states in which neither of these symmetries are broken. The strained metal in the cuprates or other systems, first it's a metal, so it preserves charge conservation symmetry, and it doesn't seem to break the lattice translation symmetry. So that's the reason for requiring that these symmetries are not broken spontaneously in the ground state. Importantly, I will not specify the Hamiltonian at all in this talk, other than to make the minimal requirement that it's a local Hamiltonian, that meaning it's a sum of operators that act on local regions of space. This includes almost all models of interest in standard discussions in condensed matter physics. There are exceptions in this context specifically, and the big exception perhaps is the SYK model that Rajdeep already asked about. So what I'm doing is not pertinent to the SYK models or anything, right? But I've already argued why I'm doing what I'm doing, right? So I'm not going to apologize further for not including SYK in my list of models, okay? I'm not going to apologize at all. I think it's good for the community to explore multiple different models or multiple different ways of thought to understand these strained metals. So what I'm doing is orthogonal to SYK. Okay, so you may well wonder, how can anybody do any useful condensed matter physics without knowing the Hamiltonian at all? And so we'll see. So we'll try to see how far we can go without specifying the Hamiltonian, right? So it turns out that we can go some distance, but clearly we can't go the full distance, right? Okay. So let's ask about lattice translations and how they're realized in the IR theory. Unit lattice translation in the UV theory, you might expect that it corresponds to an infinitesimal translation of the IR theory, because after all, the IR theory is obtained by coarse graining, right? We're taking some continuum limit, right? But this statement is a bit imprecise, and to be more precise, we should allow for action by an internal symmetry of the IR theory. right? And this nicely illustrated by a simple example by taking, say, an Ising antiferromagnet known as square lattice. The spins are arranged this way. Now, if you tune this, let's say to its finite temperature critical point, the universal physics of the critical point is described by a continuum 5 to the 4 theory. Just a standard scalar field theory of a real scalar tuned to its critical point. Now, lattice translations by one unit act on this continuum theory by flipping the antiferromagnetic order parameter. So it lets phi, they act by as an internal symmetry, phi goes to -5. Okay. Now, there may be some weird exceptions to this statement if the IR does not involve spatial coarse graining, right? But I'll set that subtlety aside as something to worry about in the future. But first, let's look at non-subtle situations, okay? So there's a very simple examples of how the UV theory provides a constraint on the IR theory in some Hamiltonian independent way. So assume that the IR theory is fully gapped and describes a band insulator, right? So we learn in elementary solid state physics, this is only possible if the UV theory has even number of electrons per unit cell, meaning nu must be an even integer. And this statement is independent of any Hamiltonian. It's just telling you that you need to have enough electrons to completely fill bands, okay? Okay, now a more subtle example, but a very famous example is what's known as Luttinger's theorem in Fermi liquids. So this theorem tells you that the volume of the Fermi surface is fixed by the electron filling in just the same way as it is in a free Fermi gas, right? So the volume of the Fermi surface divided by the volume of the below zone of the crystal is equal to the lattice filling nu modulo some integer, and the integer simply corresponds to adding some filled bands to the system, right? Now, this was proven to all orders of perturbation theory, starting from the free Fermi gas by Luttinger. That's why it's called Luttinger's theorem in the 1960s. And a very interesting non-perturbative point of view on this theorem was given by Masaki Yoshikawa about 20-something years back, who really emphasized the topological character of the statement. It's almost as though something is quantized, right? If you wish, the difference between the left and right hand side is always an integer, irrespective of the strength of interactions, right? So this is also a Hamiltonian independent statement, so long as ground state is a Fermi liquid, okay? Okay. Some quantum field theorists might think of this as a non-renormalization theorem of the kinds that people like in, I don't know, supersymmetric field theories or something like that. But so this difference doesn't renormalize. That's another way to put it. So what we have done is, so one of the things that we've done is to revisit Luttinger's theorem from a modern point of view. And we now understand Luttinger's theorem as a consequence of something deeper, right? And the deeper structure is that of the emergent symmetry of the low energy Fermi liquid theory and this property that I call the anomaly, the 't Hooft anomaly of this emergent symmetry. And then we generalize this deeper structure, and hence, as a consequence, Luttinger's theorem to strained metal phases that are not ordinary Fermi liquid metals. Okay, so that's what we've been doing. So, Kedar, how much time do I have?
Well, you have technically another 10 minutes, but you can go a little bit longer.
Okay, yeah, I'll try to wrap up in 10 minutes. Let's see how it goes. I think it should be okay. I'm not able to keep track of the chat as well. So if somebody has, if there are questions on chat, you should just let me know.
Yeah, I was looking at that. So far, nothing.
Okay. All right. So let me illustrate these connections between the emergent symmetry, the anomaly and Leringer's theorem, by talking about metals in one space dimension first. And then I'll very quickly, in a couple of slides, just mention 2 dimensions and then the generalization, and then we'll finish. Okay. So that I should be able to do that in just over 10 minutes, maybe 11, 12 minutes, I think. Let's see. So in one space dimension, so the system I have in mind is free fermions, to be free or weakly interacting fermions at non-zero density in 1D, right? So they have some sort of dispersion, and there's a chemical potential. And low energy theory, the chemical potential is here. There's the Fermi energy. In the low energy theory, you have to linearize. You have to work near the 2 Fermi points, and the simplest thing to do is and the correct thing to do is to linearize the dispersion and map this to a problem of, in the free theory, of to the problem of a massless Dirac fermion in 1+1 dimensions. So what is the IR global symmetry? The IR global symmetry is U1 cross U1. I have separate conservation of particles near either Fermi point, right? And how the microscopic global symmetry is embedded in the IR is in this IR symmetry as follows. The total charge Q is the sum of the number of left movers and right movers, while the total momentum P is the Fermi momentum times the difference of number of right movers and left movers. Okay. Now the chiral anomaly, or sometimes called the axial anomaly, is the statement that this IR global symmetry, U1 cross U1, is broken by external electric fields. And in condensed matter physics, this is very easy to understand. If I apply an electric field this way, all the particles will shift their momentum. Their momentum will increase along the direction of the electric field. So consequently, you'll deplete particles from here, and you'll increase the number of particles here, right? Which means you don't have separate conservation of number of left movers and right movers anymore. So more formally, the continuity equation for the left and right moving currents is instead of d mu j mu being 0, it's now modified, and there are terms proportional to the electric field. So this is the chiral anomaly. So the statement is that the emergent symmetry is violated by the presence of external gauge fields. And this statement is a general statement. It's a hallmark of the anomaly in general. This is how it works out even in higher dimensions. But let's see how this implies Leringer's theorem. It's a very simple argument. So if I apply this electric field, then in the UV theory, I can calculate the, I know what happens. I have Newton's law. So the rate of change of momentum is the total number of particles times the electric field. And assume I'm setting the electric charge to be 1, right? Now, let's try to reproduce this Newton's law statement from the IR theory. From the IR theory, the point of view is different, because in the IR theory, we only know about what happens near each Fermi point, right? And the momentum is kf times nr minus nl. So the rate of change of momentum is given by this. But this quantity is precisely what's determined by the anomaly equation, because that's what the anomaly equation tells me. And it gives me an answer which is kf times EL over pi. Right? So in particular, the low energy theory doesn't directly know about the total charge, the QUV, but it knows about the Fermi momentum. Right? So comparing these two statements, we find that kf is fixed in terms of n in a manner which is precisely Leringer's theorem. Right? So Leringer's theorem therefore follows from the anomaly of the emergent symmetry. Let's now think about 2 dimensions, and I'll start with the case of the Landau Fermi liquid. So in the Landau Fermi liquid, in two dimensions, the UV symmetry is U1 times charge U1 times lattice translations. And the IR theory has quasi-particles near a sharp Fermi surface, right? So there's some Fermi surface, and it's a feature of Fermi liquid theory that the number of quasi-particles at each point on the Fermi surface is separately conserved. Okay, so that's a basic feature of Landau's description. of a Fermi liquid. Now, this leads to a very large, in fact, an infinite dimensional emergent symmetry of the Fermi liquid in 2 dimensions. The microscopic symmetry is just this, but the low energy symmetry group is in fact a rather complicated group. It's what mathematicians would call a loop group. It's strictly speaking, it's a map of, it's a group of smooth maps from a circle to a circle. So that's an infinite dimensional group. So there's a huge emergent symmetry in the Fermi liquid. So the IR symmetry, just like in the 1D example, 1 plus 1D example, has an anomaly. And the anomaly is again manifested very similarly. If I turn on, say, if I turn on an electric field, the entire Fermi surface moves in the direction of the electric field. So clearly, the separate conservation of quasi-particles at each point of the Fermi surface is violated. Only the total charge is conserved. Now, it's more entertaining to think about the example of a uniform magnetic field rather than an electric field. Now, in a uniform magnetic field, the dynamics of the quasi-particle is such that it moves around the Fermi surface due to the Lorentz force. Right? There's a V cross B force on the quasi-particle, so it moves around the Fermi surface. Right? Now, this clearly means the number of quasi-particles at each point of the Fermi surface is again not separately conserved, because if I create a lump of quasi-particle here, the Lorentz force is going to kick it to other portions of the Fermi surface, and I'm going to lose my separate conservation. Right? Only the total charge is conserved. Okay. So semi-classically, at least, this quasi-particle moves around in one direction on the Fermi surface. So this feature may remind you of something. And it may remind you of something if you've been sitting in condensed matter colloquia for the last 15 years. It may remind you of edge states of an integer quantum Hall system, right? Of one of the prominent topological states of matter, right? And indeed, it's a very useful physical picture to think about this in the following way. Think about the Fermi surface as the boundary of the rigidly occupied Fermi sea. Now, in a magnetic field, the interior of the Fermi sea is rigid, but there's a chiral edge state in momentum space at the Fermi surface. So think about the Fermi surface really as the boundary, right, of something topological that's sitting inside. And the topological thing is an integer quantum Hall state, but now in momentum space, right? So this point of view can be made completely precise. And it turns out to be a very good, a direct consequence. It can be derived as a consequence of the general description of the anomaly of the emergent symmetry of the Fermi liquid. Okay. Now, just like in 1D, so I won't give the detailed argument here, but you can argue this. Luttinger's theorem, and in fact, several other universal properties of the Fermi liquid followed just from knowing its emergent symmetry and anomaly. For instance, the response to an electric field and so on. So these kinds of kinematic properties must be distinguished from other dynamical properties that require detailed knowledge of the IR Hamiltonian. For instance, things like the Fermi velocity, right? So the point is that there are some universal properties of a Fermi liquid that are Hamiltonian independent, and they're what we call these kinematic properties. They depend on general structures like what the emergent symmetry is and what the anomaly is. And there are other universal properties, the dynamical properties, which depend on the details of the fixed point theory, the detailed Hamiltonian or Lagrangian of the fixed point theory. Okay. Okay. So now let's generalize this beyond Fermi liquids. So what we argued was that compressible ground states at generic density with the UV symmetries of charge conservation and lattice translation, the low energy theory, the IR fixed point theory, must have anomalous emergent continuous symmetry, much like in the Fermi liquid or in the 1D example. first, there should be emergent continuous symmetry. And furthermore, this emergent continuous symmetry must have an anomaly, right? So the implication is that there are emergent conserved quantities O, but whose conservation is violated by external electromagnetic fields. So the level of argument is that we have physics level proofs of these statements in D bigger than 1, but in D equals 1, we have a rigorous proof of this statement, right? A math level proof of this statement in D equals 1. So this statement that the conservation is violated by electromagnetic fields will also guarantee that the electrical current will mix with these conserved quantities. Okay, so we have the emergence of conserved quantities. We are guaranteed that these conserved quantities will mix with the electrical current, and we are guaranteed that this conservation law will be violated if we turn on an external electromagnetic field. Okay, so now I'm ready to put everything that I've talked about together and conclude. So let's go back to our central dogmas, clean, scale, invariant, and compressible. So dogmas 1 and 3, which is what I've talked about so far, they constrain the emergent symmetries and anomalies of any metal, right? Dogma 2, which is the scale invariance, this is what I talked about first, it constrains transport in strange metals, okay? So when we put these together, we seem to run into a contradiction, right? The conclusion from dogma 2 was that strange metal transport is intrinsic. There's no delta function in the IR scale invariant theory. But the conclusion from dogmas 1 and 3 is that the strange metal has emergent conserved quantities whose overlap with the current is guaranteed by the anomaly, right? And earlier we saw that it was precisely this structure that enabled this delta function in the conductivity, right? So what's the solution? So the various things that I've told you are in seeming tension with each other, right? So the solution, there's only one resolution, and the resolution is that the susceptibilities of all the conserved quantities O that overlap with the current need to diverge for us to be able to get rid of this delta function. So in other words, the coefficient of this delta function, which if you recall, I said is going to be determined by thermodynamic susceptibilities, has a numerator and a denominator. The numerator is a susceptibility that is in fact determined exactly by the anomaly. It's in some suitable units, it's an integer, it's a quantized integer. So we have no negotiating power over the numerator. So then what's left is the denominator, right? And the denominator is the susceptibility of the conserved quantity O. So the denominator diverges, we can get rid of the delta function and then get just the intrinsic conductivity, okay? So what are these observables for diverging susceptibility, right? So J will overlap with all IR conserved operators with the same symmetry under GUB. Now such operators must have the same, so these operators O must have the same symmetry as J. So they must be odd under time reversal and inversion. They must have zero crystal momentum, and they must transform as a vector under lattice rotations, right? So we understand the symmetries of the observables whose susceptibility must diverge at the strained metal fixed point. And it turns out that these symmetries, these observables of these symmetries are in fact a much discussed order in the context of the cuprates. They are known as this Verma loop current order. It corresponds to circulating electrical currents within a single unit cell of the copper oxygen plane. And these were advocated by Chandra Verma starting the mid 1990s till now for other reasons. There's many reports of static loop current order in the underdoped cuprates in the pseudogap regime, and there are also many controversies. I don't really want to wade into the controversies at this point of time in my work at all. But what I think we do is to give a completely different rationale for critically fluctuating order with the same symmetries as this loop current order for reasons in the strained metal regime, without necessarily committing to whether this order exists as a static order or not in the underdog side, right? So the rationale for the importance of this order for us is completely different from any of the reasons that Verma has given over the years. But nevertheless, we seem to end up with the statement that this kind of order is, at least in its critically fluctuating form, is important for various reasons. So anyway, so that's the end of my talk. So let me summarize that I made a few basic assumptions that I stated as dogmas, which lead to strong constraints on the IR theory that must be satisfied by any putative non-formal liquid. Right? So obviously we haven't constructed the actual theory. I didn't even write a Hamiltonian Lagrangian of the UV theory, let alone the IR fixed point theory. But what we can get are strong constraints on the shape of that theory. Right? And amazingly enough, these constraints lead to model independent statements for experiments. We can make statements, very concrete statements about divergence of some susceptibilities. So the general question, how far can we go without actually writing down a model, right? Clearly, this is the easier part of the problem to solve. And I hope to be able to solve this problem of milking this model-less general development as much as possible before taking the harder problem of writing down and solving models. All right, let me stop.
Thank you, Sanatan. That was very nice. Questions? Asdeep?
Yeah, one question, Senthil. You also pointed out that there's strong evidence for non-Fermi liquid near magnetic critical points. You showed us data from QPRES also, and then sometimes the people also have seen sublinear temperature dependencies. I mean, depending on whom you ask what those numbers are, but often less than 1. Would you have CCO? I forgot the exact thing, but anyway. So does this general structure even hold for near magnetic critical points, let's say, what you are saying?
I mean, since I've made almost no assumption about any of that, right? As I said, my only assumptions are that it's clean, translation invariant, and compressible. Very mild assumptions, right?
But your GUV might be at least close to being broken, if not broken, right? I mean, GUV probably has a spin symmetry. In that sense, I was trying to see how important is that aspect.
Oh, that for nothing that I say, that it certainly doesn't matter if I have critical fluctuations. That's a non-zero wave vector.
Yeah.
Right. Because the quantum critical ground state itself is translation invariant, right? After all, even a Fermi liquid has power law correlations at 2kF wave vectors.
Mm-hmm.
Right? Or the 1D Böttinger liquid has power law correlations at 2kF.
Mm-hmm.
Yeah, so that doesn't matter for what I'm saying.
You're saying as long as you're on the other side of the transition, shouldn't worry.
As long as you're at the critical point or the symmetry preserving side, these statements are true.
Other questions? Vikram, anybody else? If not, I had one about the 1D case. So there, presumably, there is no conflict because at least in the standard Luttinger liquid, conductivity does have a delta function, or am I mistaken?
Right. That's right. No, that's absolutely correct. In fact, these anomaly arguments give you the exact delta function.
Right. But is there a possibility of a different 1D state where there would be a tension which would be resolved by this kind of susceptibility diverging?
Yeah. So it's definitely possible to contemplate a model in which you have a divergence of this of the susceptibility, right? So we didn't pursue the 1D constructing a 1D example that much, but we have examples in 2 dimensions, or
Mhm.
where you get a suppression of the delta function. Um,
Right.
Actually, in the model that Kedar, you probably know quite well, it's the so-called quantum Lifshitz model.
Mhm.
So if you think of that as a model for a phase transition between a boson superfluid or ordinary boson superfluid, and one at where the superfluidity is at non-zero momentum.
Right.
So then at that critical point, you get it's described with this quantum Lifshitz model, and it's the critical point is compressible translation variant, preserves global U1 symmetry, but
Right.
there is no delta function.
There is no delta function. Right.
In fact, it's insulating.
Mm-hmm.
So it's very weird. It's a compressible insulator at the critical point.
Right. Right.
And you can trace it to precisely this kind of reason.
This kind of susceptibility divergence. Right. Okay. Other questions? Let me just look at the chat once.
Kedar, if there are no other questions,
Sure, please go ahead. Please go ahead.
That is. So Senthil, you had, I remember in earlier you had thought of, critical non-Fermi liquids in a way where, the Fermi surface kind of existed, but let's say the quasi-particle residue went to zero.
Yes.
So the susceptibility divergence, which now gets rid of your delta function in the transport, would it also lead to, for example, similar vanishing of the Z factor, but keeping the Fermi surface alive?
It's hard to say, right? In a sense, we're trying to tie our hands behind our backs to some extent by not specifying any model, trying to work in this very general setting. So the power that we have is limited, right? So will this destroy quasi-particles by itself? Hard to say. Right?
These are weaker assumptions than you probably need for.
Yeah, these are much, much weaker assumptions, right? So the amazing thing is that after making these extraordinarily weak assumptions, we're able to draw any strong conclusions at all. Right? But
right.
Leringer's theorem is a strong conclusion, and the fact that Leringer's theorem is a sub-statement of a more general statement about emergent symmetry and anomaly. Right? So I think that's the really important statement, and the general symmetry and the emergent symmetry and anomaly are strongly constrained by just assuming that it's clean and compressible.
Right.
So you can think of it as a big generalization of Leringer.
Other questions? Anybody? Wonderful talk.